Okay, for this laboratory activity, this is activity B for introduction to DC voltage sources. And what we're going to do is we're going to look at an old desktop power supply. This is the old power supply that goes in a desktop. Let me get another one over here. Here's another style power supply. You can see from the back side how you recognize that on the back side of your computer where you plug it in. They have a cooling fan, and there's all different kinds of styles. Now this is a really old one. It happens to have something called a negative 5-volt rail, and the newer ones do not. But anyway, look, we're gonna examine this, and I think you'll have a little fun. And the beauty of these is, if you wanted to set up a little electronics workshop, you could get away with using this for a lot of little projects. It's a really handy little thing to have. They're cheap. People throw them away. And you can use them for a lot of things, and I'll talk some about that as we proceed. Now, the first thing you might want to notice is that I'm going to turn my meter to measure AC voltages. And notice that we have to plug this into a receptacle, and if we measure that, you might want to just know that your AC voltages in your home, this is called US mains. Around here, so we see it's about 125 volts or so AC. So that's an AC voltage. It's a voltage that changes polarity 60 times a second. The frequency is 60 hertz. Now, what happens is this AC voltage comes in and there's it steps down the voltage and converts it to DC voltages like a battery where the voltage is constant and steady. And on top of that, there's a variety of rails. We call them rails, voltage rails, different voltages. And if you think about it, these are very, very useful voltage values because think about this. When you buy a computer, it's got a lot of common electronic elements in it. For instance, you're going to need a plus and minus 12 volt rail to power a bipolar op amp, an operational amplifier, and your integrated circuits and things like that. These are very popular voltage rails for various electronic components. Now, by the way, for instance, you might know that your USB supplies 5 volts. Well, this red wire here, that's the 5-volt rail. So that comes straight out to your USB. Of course, it's regulated more highly and also current limited. But nevertheless, that's the basic idea. Now, how are we going to do this lab? So what I'm going to do is, first you should look over it and understand that when you talk about electronics, you usually just talk about nominal values. A lot of times when you design circuits, you don't really have to be exact. A lot of things you just get in the ballpark values. But there are some projects where you need precision values. But anyway, so when you're talking about a computer power supply, a PCPS, personal computer power supply, we have, this is an old one now. Like I say, some of these newer ones don't have a 5-volt rail, but you've got the voltage rails. You've got a blue, which is negative 12 volt, white, negative 5. The black wire is ground. So that would be like a 0 voltage. That's actually tied to earth. That's 0 volts, ground. And then the orange is positive 3.3 volts. The red is positive 5 volts, and the yellow is positive 12 volts. Now those are nominal values. They can vary significantly from power supply to power supply. And I've got that on your lab manual, these nominal values up here. So what you need to do is take those nominal values and fill in this chart. See I've got a little sign here, nominal values, and then you fill in this chart based on what the potential difference would be if you measured it with a multimeter based on those values. And on the second page are some examples of what you would see. So basically, for example, if you, this first one right here, if you put the red probe on the plus 12 volt rail and the black probe on the plus 5 volt rail, you would get, what you do is you take the red probe and subtract off the black probe. Because what you're doing is you're measuring a voltage drop, a change in voltage. So that would be 12 minus 5 is 7. So a plus 7 volt difference. And what's interesting about that, in your first semester physics, you might have been exposed to the idea that there's really no such thing as zero potential energy. You just define it somewhere to be zero that's convenient to solve the problem. basically you can only measure changes in potential. So in electronics, that's like a voltage drop. Now, you might not have ever thought about this. Not only is there not really such thing as a zero potential energy, there's really no such thing as a zero kinetic energy. Because in your first semester physics course, you always just assumed that there was a reference frame with respect to you that was at rest, that had zero velocity. But that's really not true, right? I mean, think about the Earth. We're spinning on our axis. We're moving about the sun. Our solar system's moving. Our galaxy's moving. And the galaxy that's located in a supercluster of galaxies, it's all moving. So we're moving. There's no center of the universe. So we can really only measure changes in energy. And voltage is related to energy, as we'll discuss later in the class. So we have electrical potential, which is voltage, is related to electric potential energy, and we'll define that later. Okay, now let's look at the first thing we can do here. I hope you are kind of grasping what I'm talking about at this point, but it's a little bit abstract. But let's get back to just some very practical stuff here. So what I'm going to do here is I'm going to show you these values. These are your nominal values. Okay, now let's get the real ones, and I've already filled them in here where it says measured values. I'm going to show you how you do that. We're going to put the black probe on ground. Then we know what every rail is, every voltage value with respect to that ground, that 0 volt level, which is tied to Earth. And you can read about that if you'd like to look it up. You know, what's a ground? What does that mean? Okay, now watch this. I'm going to start with the yellow wire. Let's start with the blue. Let's go in order. So if I put it on the blue, if I touch the blue rail with the probe, we see, whoops, I got it on AC. Sorry about that. I got to put it on DC voltage. I'm glad I did that so you can see. You got to have your meter configured correctly. Okay, so basically we see, whoops, that's the wrong rail. I got black rail and blue rail. Making all kinds of mistakes here. Okay, negative 11.04 volts. Now notice it's changed a little bit. These values can drift. So I had a negative 11.05. That's okay. We'll just stick with it. Okay, so, there we go. Well, there we go. Negative 11.04 volts. Okay, now let's go to the white rail. That's the next value. Okay, see, it's not really negative 5. It's negative 4.57, negative 4.58. Or see how it's drifting a little bit? So anyway, that agrees with what I measured earlier. Okay, now let's go to the positive rails. The 3.3 volt rail is, I just rounded that off, 3.29, so that still agrees, plus 3.29. The red rail, or the 5 volt rail, nominal 5, it's actually 5.35, and that's pretty common. I've noticed that a lot of computer power supplies, generally the voltage rail on the red is generally higher than 5, like that's a normal value. I don't know why we even call it a 5 volt rail. Okay, anyway, so there you go. And then the yellow rail relative to ground is plus 11.95 volts, and that agrees with what I wrote down earlier. I hope you can see all this. Okay, now, so what you're going to do first is you're going to take the nominal values. The nominal values, that's negative 12, negative 5, 0, plus 3.3, plus 5, plus 12. And you're going to fill out this table to predict, based on nominal values, what those potential differences would be. In other words, we're doing combinatorics, every possible value of voltage you can get by just every possible connection. So it's just going through all possible combinations. Now look here. This page right here will explain how you do that very well. It's very straightforward. I'll check and make sure I didn't make a typo there before I load it on Canvas. And then here's some examples you need to notice. Here's a bar graph kind of showing you another way of looking at this. You see a bar graph with respective voltage levels, positives. You see 12 is bigger than 5, bigger than 3.3, and then you go negative. Anyway, you can basically, if you put the red probe on minus 5 and the red probe on plus 5, what would that give you? Don't forget your units there. Okay, so you got to do, there's 3 little examples that you can do. Now, in these tables, you can leave the volts out. I made the font size 9. You can leave, why can you leave it out? Because we specify that all the voltage differences are in units of volt right there. So that takes care of our units. You really should write them down if you're not used to, carrying units. You really, in a lab, you need to watch your units. We're not doing number theory. This is physics labs. Everything has units. All right, now, let's do this table here. Okay, so this table, the first table, the nominal table, you can do just theoretical values, nominal values. Now, we don't really expect these to agree with the measurements, okay? Now, this is the table where you're going to have a little bit of a headache. I'll tell you why. It's not that bad, though. It's pretty easy. Basically, I want two values in this table. The first value is going to be the one we measure. So you're going to have to get out a piece of paper and get, and a pencil and take some notes and write these values down, because I'm not going to do them all for you. So the first value is the value we measure, and the second value is the value you calculate based on the measured values from here, where I measured each individual rail with respect to ground. I measured each rail with respect to ground, and those are those values. Now, so let me show you how I'm going to do this. This is very, very methodical. I got everything laid out perfectly. We're going to take the black probe, we're going to work this way in rows. If I put this on blue, see, black lead on blue, then I can take my red lead and I can go blue, white, black, orange, red, yellow, right? So I'll do this first one. So this first one, we get, well, actually, look, blue to blue is first, but that should be 0, and it is, basically. See that? 0. Why? Because, well, there's no potential difference between its own rail. Now, let's go to white. So we got red lead minus black lead. So basically, if we measure it, we straight up get 6.46. Now, earlier I measured it and got 6.47. I'm just going to leave it. These things drift a little bit. Now, if you calculate that, what should you do? So remember, I'm going to leave it there. We've got the red on white, red probe on white, and black probe on blue. So basically, we go up here and we take what? We take the red probe that's on the white. So the white is negative 4.57. I'm going to negate that. And then you're going to subtract, you're going to subtract negative 11.5. So we're going to say minus 11.05, but you got to negate it, so it's like adding it. And indeed, you get 6.48. See that? So we go down here, and we see that that is indeed the case. I wrote that in for you. Okay, so let's finish this row up. So basically, we got the black lead on blue. Now, I already did the white. Let's go to the, okay, that's just blue with respect to ground, right? We get 11.04 because it's 0 minus a minus. 0 minus, you see that? So it gives a positive value. So I'm going to put that in there. 11.04. Now, you have to go in there and calculate it and see what you get. Okay, now, orange. 14.34, right? Red, 16.39. Remember, I'm keeping my black lead on the blue rail. And then yellow. Now this is the biggest potential difference you can get. Do you see that? This is the largest potential difference that you can have. Why? Because this is the maximum voltage and that's the minimum voltage. So that's the maximum delta. Now what happens if I just swap the leads? Predict what will happen if I swap the leads. We should get the same value but negative, right? So that's the biggest potential difference that's negative. Now, okay, now let's just, so now I'm going to put commas in here. Now what do you have to do? Beside that, you have to go up in there, go up at the top again and calculate based on the measured values with respect to ground. Just take differences, right? Red probe minus black probe. Now, that's pretty straightforward, I hope. Now, I'm not going to write down anymore. You should be able to watch this video and pause it as needed and do the rest of them. So let's be real logical about this. The next thing so you need to be writing this down from here on out. So you can stop the video, get a piece of paper and a pencil ready. Okay, here I go. Now, the next, we're going to put the black on the white. Okay, now pay attention. There we go. Now, we start with blue. So, you see that? You should be able to see it. Black on white, red on blue. Negative 6.46. White to white, 0. See, I'm just going straight across the row here. White to black, 4.58. Orange to white, I'm saying red first, 7.87. Red to white, 9.93. Yellow to white, 16.54. 16.54. Okay, now we take the black and we move it to black. That's ground, right? That's where we are now on this row. We're on the third row. Okay, blue. Now that should be negative 11.04, something like that, right? Whatever we measured. Yep, negative 11.04, see? So we got black, blue to black. I'm doing red to black. Blue to black, negative 11.4. See, these are negative rails. White one, negative 4.58. Whatever, it's changing. Okay, now, 0 as it should be. Black to black is 0. Okay, it's just both probes grounded. All right, now, orange to black. That's just the value of the orange rail, right? You can round that off to second decimal place, 3.29. Red to black, 5.34. See, we already measured these, really. That's why I got that star there. We measured those up there. This is the exact same thing that was at the top of the page, but I'm doing it anyway so you can see it. And then yellow to red, black. Yellow to black is 11.95. Now we're going to move the black to the orange. So we're on this row, right? Now I already did one of those. Okay, blue to orange, negative 14.33. White to orange, negative 7.87. Negative 7.86, whatever. I don't care. Either one. Okay? Black to orange. This will be negative, right? Because we've got our blue. It's the negative value of what it was when we had the leads the other way. So negative 3.29. Okay, now we're going red to orange. 2.057. Yellow to orange, 8.67. Okay, now, the red probe. Black on red. We're right here, this row now. Okay, blue to red, negative 16.39. White to red, negative 9.93. Black to red. Now what should that be? That should be the negative of, what was it, 5.3 something? It should be negative 5.3 something. Yeah, negative 5.34. Orange to red. That's a small difference, right? Minus 2.06. Orange to red, minus 2.06. Now this should be positive again because now the yellow is bigger than red. So like 12 minus 5, somewhere in the neighborhood of 7 volts, right? Something like that anyway. That's 6.6 volts, 6.60, yellow to red. Okay, we're on the last row of our table. Now we're putting the black on the yellow. Now obviously this should be a minus. This is one of the largest numbers, but it'll be minus because this is negative minus, a negative value minus a positive value will be negative. That's a big change. Minus just negative 23 volts, right on it. White to yellow, negative 16.53. Black to yellow, negative 11.95. Orange to yellow, negative 8.65. Red to yellow, negative 6.60. Okay, so that concludes the table. Now you should be able to finish this based on if I send this to you. Now, I just want to make a couple more comments. These computer power supplies are useful for other reasons too. For example, the positive rails will deliver a pretty substantial amount of current. So if you ever, your car battery is 12 volts. An old car battery is 12 volts. Now notice we have a 12 volt rail here with significant power. You could buy a cheap audio amplifier that goes into your car and you can hook that up to the yellow rail and that'll power an audio amp. We do that a lot because audio amplifiers are useful for working with low frequencies when you need power to move something, in an AC fashion, something that changes, some movement like a piston or a speaker or something. Okay, now one thing you should know is the negative rails are current limited. They don't deliver much, so they don't have high power. They have low current. So the blue and white, the negative voltages you can't really get They don't deliver substantial current at all. Now, something else that's useful is these little modules here have become popular. They're made in China, of course. This is basically a voltage regulator circuit that's already built on a board. They come as like a perforated board. You just snap them off. And basically, it's kind of interesting. You hook this up to the largest voltage I have is 12 volts. And you can actually, let me see what the polarity is here. I don't know. Okay, that's let's see. Okay, that's negative. I need to go this way. Okay, so there you go. Now, notice that that's about the largest voltage you can get out of it, because when you're regulating voltage, you kind of get a drop down from what's available. So we know we have about 11.9 or whatever it was volts here. It drops it down about a volt. That's called a dropout voltage. But check it out. There's a potentiometer on here. That's a variable resistor, and you can take the potentiometer and adjust it. It's kind of a pain. And watch, basically you can control the voltage. Damn, this is aggravating. These little screws. I usually weld a little knob on them. See that? And you have a lot of control. I can't keep the screwdriver in it. There we go. It's a potentiometer. We call them pots. See that? How I'm dropping the voltage? You can go all the way down to about 1.5 volts, maybe 1 or 2 volts. You can't go to 0, but see that? Now you got an adjustable voltage like a real benchtop power supply. Like I say, that little module cost you about $1.50 on eBay. See that? I'm changing it. Now it's real aggravating, but believe me, I'm not going to sit here and do this forever, but let's see if I can if I can turn it a lot, we can really drop it down. There we go. See it dropping down? Believe me, that'll go all the way down to about 2 volts. But anyway, that's kind of nice to have. So there's lots of things you can do with a computer power supply. So I hope you appreciated this, and hopefully you'll, and basically if you ever have one go bad, you'll know there's not much to it. You can just pop it out of the computer and put a new one in there, save yourself a bunch of money. Now another thing, one more thing. To use it like this, you've got to trick it, sort of. You've got to make it think you've got it switched on. This one has a double switch, but there's a green wire on all these wires, and you have to basically strip them down, and then you have to ground it. You have to connect the green to the black, and then put a wire nut or some heat shrink or something, and that way you've got it permanently connected there. So the green wire has to be grounded to the black wire, and that way it stays on. Okay, hope you enjoyed this video. Thank you.